So the STRAHL is a transport code which comes from 80s. It was first written by Beringer, now it is maintained mainly by Ralph Dukes. It's a 1D transport code for the impurities. What it mainly do, it solves the transport equation using a ionization or combination rates from the ADAS database to get the time evolving profiles of the impurity density for each ionization stage. It also includes a NeoArt module to calculate a neoclassical transport, and also, it depends, as I said, on the ADAS atomic data to calculate a suffix radiation or any line radiation which is needed. And this tutorial will show how to use it for a basic analysis of the data. Like I will start from the basic analysis to the more advanced, like investigation of the laser blow injection. So first, just import the module. Now it is in unstable branch. Unstable. Also, I will import a module which will give me a kinetic profiles, for example, ZipFit. Load the kinetic profiles. I'm studying discharge 175 A60 because it's the one with the laser blow injection. Extra zip profiles from MDS Plus, and now STRAHL. First, you can set up the device, but now it is working only on D3D. It should not be difficult to generalize it also for other machines, but there was no interest yet. You will choose the shot, the time. These numbers are required only for selection of the equilibrium, and the EFIT 3. You can load EFIT from NDS Plus or from external file. So I will choose just EFIT 01. Then you have to prepare a STRAHL grid file. That's the special format which is needed for the STRAHL to read the equilibrium from the EFIT equilibrium.
So STRAHL to run needs an equilibrium?
Yes.
And then what profiles does it need?
It needs also kinetic profiles. There are two options. I will show it. So first, you can specify the kinetic profiles by an analytic formula, or you can use experimental profiles. I will use experimental and choose ZipFit. So it will load electron temperature, electron density, and if available, also ion temperature. The ion temperature is not needed. It's used only when you calculate a neoclassical flux.
What profiles modules will work with this?
Yes, you can use OMFIT profiles, ZipFit, kinetic EFIT times, OMFIT 1, 2, and QuickFit.
Well, that's pretty.
Everything.
Almost everything. Also, if the profiles are rolling in time, you can decide if there will be averaged in time and constant, which can make the simulation also faster, or you can use time evolving kinetic profiles.
And maybe just more as a background. So in STRAHL you have the core plasma,
yes,
right? And then you have the scrap-up layer.
I will explain this. I have a special slide to show it more in detail. And also, yeah, you can decide if you will use the data outside of the Life's closed flux surface, or it will be extrapolated by exponential decay. Because our data are really good, I will assume that, yeah, that's okay. So the next step is the name list. This part just set up the name list for STRAHL, and it should help you. It should simplify it. So first you can specify the time range when you will run the simulation, the time step. Then the main ion impurity, the main ion, and the impurity. There is several options. Aluminum, argon, up to the tungsten. If you want, you can add more impurities than just one. In order to keep it simple, I will just introduce one, carbon, which is the main impurity on D3D. The next, you had to specify the atomic data. It's flux for, these are flux for STRAHL, what it should calculate. If I need a main ion Bremsstrahlung, suffix radiation, spectral resolve Bremsstrahlung, I don't need this one. I want to calculate the thermal charge change. In order to calculate the thermal charge change, I have to also specify the neutral density, which is not measured, so okay. I'm not using this option. Or NBI charge change, for this you need to specify neutral density and the distribution function of these neutrals. And then, if necessary, you can calculate also some diagnostic lines, but this must be specified. It's not so easy to use them. And on the second part of this, you can specify which atomic data will be actually used. There are several options for the elements. Most of the time they are almost the same, the atomic files. But if you want to compare them, there is a button show, which will plot all of these files together. And then you can switch to another and simply compare them. There is a line radiation suffix range, continuum radiation for each ionization stage of carbon.
So these files are atomic data coming from different sources?
From ADAS. So
it's always ADAS, or it could be some?
I think it's always ADAS, okay. Most of the cases. Recombination rate, the continuum Bremsstrahlung, that's the filter function for the suffix ray camera we used. Mm-hmm. Fractional abundance in the coronal equilibrium. Cooling factors, how much it radiates, how much one single atom radiates as function of temperature in the coronal equilibrium. You can see the dashed line is the total radiation, the full line is the suffix ray, total suffix ray radiation. It's growing a lot above 1 kiloelectron-volt, which is mainly due to the Bremsstrahlung. And the last is the relaxing time. It gives you the time which the impurity needs to reach equilibrium in the fractional abundance. If you change the ion, if you would do a perturbation in the fractional abundance of the ions, for example, by throwing there lots of neutral impurity, it will take roughly about 20 milliseconds to reach 20 milliseconds for carbon to reach equilibrium at 100 electron volts. Yes. The next option which you had to specify is the impurity source. There are several options. First, you can assume time-independent source. That's just how many particles per second will enter the plasma. Or other option is time-dependent source. In this case, there is several source function. You can use gas path, and it will load the gas path from the MDS plus for D3D. Or you can specify directly the data points. Here's example. You can always preview the source function. There was some localized source of carbon, and the last option is the synthetic LBO source function. Okay, it's roughly the shape of the source function we have observed after the impurity injection by fast cameras. So you have to specify the rise time, the fall time, the number of particles, and the time of the injection.
And I saw that under the ions tab, you had something about the energy.
Yes, that's the neutral energy. With the particles are entering the plasma, it's assumed that they are entering its neutrals with certain velocity. If they are faster, they can penetrate deeper. If they are slow, they can, but in most of the time they are ionized very, very close to the scrape flyer. They never, maybe in very low density discharge, they could reach the core, but I don't, so they are ionized very close to the edge. Yes, impurity source, the recycling. That's probably the most difficult part and also the most interesting. The border decay length is just a numerical parameter which should not play a role. If it plays, then you have done something wrong. It tells you, it tells STRAHL that outside of the last grid point where the impurity density should be already 0, how fast the impurity decays. Then the recycling, I will explain these three numbers using a presentation I prepared. So STRAHL edge and recycling model. It's a very simple 1D model. It depends on several parameters. Scrape-off layer width and limiter shadow region width. The plasma is divided into limiter shadow, scrape-off layer, core, and then there are three other reservoirs: divertor, pump, and the wall. The essential parameters is the width of this layer, width of the shadow layer, scrape-off layer temperature, Mach number in the scrape-off layer, and the connection length, or the parallel connection length, how long the particles have to arrive along the field line before they reach the divertor or before they reach the limiter. Then the pumping time, how fast the particles are going to the pumps, and the divertor to scrape-off layer, how fast the particles are coming from the divertor back into the scrape-off layer. And the recycling coefficient and edge decay time length. And I will show them what are they actually doing. So first, the particles from the source enter the plasma. They are propagating from the edge over the scrape-off layer into the core. Some particles, if they can exist in the core for a certain time, and then they are leaving again over the scrape. In the core, they can move only the radially or radial perpendicular to the magnetic flux surfaces. In the scrape-off layer, there is also a parallel transport. The parallel transport is given by this connection length, the Mach number, and thermal velocity. So yeah, the particles are then from the scrape-off layer are leaving, and they can enter the divertor reservoir. From the divertor reservoir, the particles can go into the pump, and the particle flux is then given by number of particles in the divertor divided by number of particles by the pumping time. Could I have the amount, or do you think that they can see it?
We cannot see it, like nobody can see it. You can try, but
yeah, okay.
Yeah, it won't go into the recording, but you can
okay, I will say. Other option, the particle from divertor can go back into the scrape-off layer, and the flux is given by tau diff to scrape-off layer, which is shown on the left bottom. The particles which cross the scrape-off layer radially can be still lost in the limiter shadow. The connection length in this part is much shorter, so the parallel losses are much higher, or they can still cross a limiter shadow and reach the wall. In both cases, the particles go into the wall reservoir, and from this reservoir, they can recycle back into the plasma as a source, and the number of particles which is recycled, or fractional particles, is given by R. That's the recycling coefficient. Okay, so let's go back. STRAHL. In this case, for carbon, we have set the recycling coefficient to be 1. It's maybe not entirely true, but on the other hand, some carbon will be sputtered from the walls, so it's difficult. And the tau divertor scrape-off is just 1 millisecond. It's really a guess. Divertor pumping time is 250 milliseconds. These numbers are not well defined and not easy to measure.
Maybe you can comment now or later. How much the STRAHL simulation depends on these parameters?
It really depends. If you are studying gas injections, they are really important. They define the confinement time, the decay time of the impurity.
Okay.
So because if you have recycling, 100% recycling impurity, the only way how the impurity can leave the plasma is by pumping. So this divertor pumping times more or less determines is the minimum for the confinement time of this gas.
Mm-hmm.
And the same with the divertor scrape-off layer. It's increasing the recycling. If the particle goes to the divertor, they are almost immediately recycled. In this case, almost nothing is going back into the pump. Yes, in the transport. You can specify first if you want to calculate a neoclassical transport coefficients, and in addition to them, you can specify the anomalous transport, or you can completely turn off the neoclassical transport and define your own transport coefficients. I will show you the second option. There is several ways how to define the transport coefficients. You can use a linear interpolation between several nodes. You will specify the position of the nodes and the values on the nodes. Here is the example. You can always preview, or you should always preview the diffusion coefficient before you use it. Small in the core, increasing to the edge, and small on close to the escape amplifier. The other option is spline, smooth, but else it is the same. The function and function 2 is asymmetric Gaussian. The actual definition you can find in the STRAHL manual, but the first number, also it is described here, the first number is the core diffusion coefficient, the second number is the escape amplifier diffusion coefficient, the third number is the maximum here, the 25 is the width of the Gaussian on this side, 3 centimeters is the width of Gaussian on the right side, and 0.95 is the position of this maxima.
Mm-hmm.
It can describe at least the very basic profiles which are observed in the plasma, but I prefer to use splines. The same you can do for the drift function, for drift or for pinch. Can described by spline. Yeah, and the last option is also D and V dependency, where the D and V are coming from a TGLF code or from anywhere else, from other codes. So drift can be also defined by the function I shown before, but you can also select a constant concentration. It will assume that the concentration of the impurity, it will find the drift such that it will give you a constant concentration of the impurity in the plasma. So let's select the spline. Drift type. The drift can be defined by several ways. It can be B over D normalized by charge of the impurity, which is motivated by the fact that neoclassical transport is proportional to the neoclassical pinch proportional to the charge. Or a drift parameter, it is V over D multiplied by R and some scaling factors, or the velocity itself, the drift velocity. Again, you can preview your function. I'm using a spline, it's 0 everywhere. Let's make it more interesting and do some peaking in the core. Yeah, you can see the difference. Now there is a significant peaking because I've introduced a negative pinch in the core of the plasma. And finally, the preview stationary profile gives you estimate how the stationary profile will look like if you will run the experiment long enough. It should reach this shape. It's very big in the core. And the last option are the sorties.
And the stationary profile assumes zero source.
Exactly. The stationary profile assumes zero source. So it's not really valid outside of the last closed Planck surface, where is a finite source. But inside, if you will study a stationary case, it's exactly equal to the final profile of the total impurity density. So in the sorties, you can specify the mixing radius. It's up to where the sorties will affect the plasma. Right? The radius up to where the plasma will be flattened. So let's say 20 centimeters is relatively large sorties. And 1.5 seconds.
And it's interesting, the mixing radius is in centimeters, it's not in rho.
Yes, internal coordinate for STRAHL is in meters or in centimeters. Rho is just used for the conversion back into the, like if you want to compare the experiment. Now we can finally run it. First, it will prepare the plasma kinetic profiles, then the impurity source, then the name list, then the atomic data, and finally it will run the STRAHL. Okay. When the run is finished, there will be a new tables. Is a viewing results and minimization. in the view results, there is option to look on 1D profile, time evolution of some quantities of interest. So I have done the LBO injection in the middle of the model of the investigated time interval. No particles are on the wall because all of them are recycled. Here is the number of particles in the divertor, number of particles in the pump, number in the divertor, parallel to the divertor, like all of these quantities which I was showing you before when I was explaining the edge model. And on the right is particle conservation. It's showing the particle conservation. In this case, it was not particularly successful. The dashed line is the total number of particles in the system, and the dashed dot line corresponds to the integrated source. And you can see that they do not match. So there is more particles in the system than I have injected, which is caused by a probably low spatial resolution or low time resolution, which can be increased, or by transport coefficients.
So you want the two dashed line to be the same?
Yes.
And is it normal that they start off different and then they converge, or they should always be the same?
It should converge, it should be equal, at least for low Z impurities. For tungsten, it's almost impossible to get them equal. Okay. But they should not differ by more than 10-20%.
Okay.
The other option is the charge state distribution. Yeah, I will use another source function. This one.
It's a very fast code, huh?
Yes, it's a 4-turn code. It's really fast, at least for carbon. When you do a more advanced simulation for tungsten, which has 74 ionization stages and needs much higher spatial resolution, much higher time resolution, and you do it with time varying profiles with all outputs, it can take about a minute. But yeah, for carbon, it's just seconds or less. Yeah, now there should be also some LBO or some sort of crash. So in the middle, you see the profile has flattened and then it's increasing again after the sort of crash. You can also look on the total density. Here there is several options what one can look on: electron density, electron temperature, all inputs, diffusion coefficients, diagnostic line, impurity density, radiative power, and soft X-ray. And one of the options is the total density, which is shown here. The time evolution, you can see that there was this large sawtooth crash which has flattened the density, then it has recovered, and it's continuing like nothing happened. Or here is the radial profile. You can see it has flattened. Well, how the flattening works is a very simple sawtooth model, but for the basic studies, it works fine. The transport coefficients, here's D, which we have specified, V and V over D, the ratio of them. And now let's go for the minimization. There are two possible workflows. First is demo, the second is experimental. In demo, there is several training examples, and I will go through few of them.
So maybe can you say something about minimization? What?
Yes, you can choose almost arbitrary parameter in STRAHL. It will just run a minimization code of your choice to find the optimum with respect to any diagnostic which you had also specified.
Okay. So it's kind of a running STRAHL in reverse.
Yes, exactly. The STRAHL itself is a forward code. For the transport coefficients and all parameters which I have shown, it will calculate the impurity density. But usually you have the impurity density and you want to know what was the transport coefficients. So you want to solve the invert task, that's not the main, like the STRAHL itself is not doing it. This module is above the STRAHL, it's running it in a loop to find the optimal solution. And as I will show later, you can also use Monte Carlo methods to find the actual distribution function for these unknown parameters. So let's go, for example, to first you set up just set up demo. Here are some outputs. So I will vary on the page profile and only one coefficient in the page profile. Shown, if you click on the convergence showing chi-square, which we have not done the minimization yet, so there is nothing. The D profile, it's the same, and the V profile has been changed. Like that's the on the top, the upper one is the original, and the dash dot is the perturbed pinch profile, and we will try to run the minimization and find the original value. And on the bottom is the fit overview. It will show some artificial charge chain data, and you can see that something like artificial measurements do not match the predicted impurity density. We will try to find such coefficient of P, which will optimize, like minimize the difference between these two. So minimize, restart. It's done. It was fast because there is just one free parameter. Convergence, you can see it has jumped almost immediately to 10 to minus 14. There is no noise, so it's relatively easy. And I have recovered exactly the original profile. It's cheating because there is just one free parameter, no noise. So let's go to a more complicated case. There will be three sources, one diffusion, one free parameter in diffusion, one free parameter in pinch. Convergence. D has changed. You see, the original profile is dashed. Dash dot is the something like the starting point. D has also changed. The over D is changed, and fit overview. It's different. Both profiles, not very significantly, but they are different. Restart. In order to run the minimization faster, it's using Marquardt Marquardt method, and it's calculating Jacobian in parallel. All gradients are calculated in parallel, so it's faster than this.
This is something special that you wrote?
Yes. It's not default. We can add noise. And in this case, there is some low level of artificial noise and something like LBO injection of carbon. You can see that it's nice. It's experimental. The model, experimental profiles with error bars, not much error model. The same for the radial evolution. You can see that it's relatively different. And the profiles are perturbed in the same way as before.
So the idea of this demo workflow is that it shows you what you can do.
Yes.
And then you will start from here, and
I will go soon to the most complex case. Okay. And the most complex case is the super simple case. Simple, like it's still much easier than the real experimental one.
Okay. Okay.
In this case, the chi-square is not going to 0, it's going to 1.1. It's chi-square normalized by number of degrees of freedom, and for Gaussian noise, it should go exactly to 1. It's close enough. You see that V was not reproduced exactly, but still it's very close to the original profiles. And we can also look on the transport coefficients with some estimate of the uncertainty. But only assuming our model, you see that there is some uncertainty in V. D is very well defined by these measurements. The here is D, V over D, V, and the stationary density profile. There is also small uncertainty, but there is just one free parameter and Gaussian noise, so it's very well defined. And almost a real case.
Almost real.
Yes, in this case there is a noise and all coefficients in D and V was changed. Here's example. You can specify the parameters. First is anomalous D, anomalous V. You have to set their values. In this case, it's described by two asymmetric Gaussians. You have to also specify the minimum and the maximum for all of these parameters, and which parameters will be varied in the minimization, and the same is for the V. And so, in order to find an optimum, you don't have enough measurements to minimize all parameters. It's usually best to start with the most important ones, which contributes most, and that are, for example, the first three parameters, which define the core, escape outlier, and the maximum diffusion coefficient, and the pinch. That's feasible. So we start, and hopefully we'll find some solution. Yeah, I have not shown the fit, how it looks like. So it's completely off. You see the model and something like the measurements, they are very different. So it's...
The initial guess is very off.
Yes, the initial guess was by purpose very, very off. But it's converging, it has already almost converged now. Yes, solution was found. So it has, optimum is 1 point, the normalized chi-square is 1.2, so it's very close to the actual minimum. D is not exactly matching original D because I was not minimizing also all parameters, just 3 of them, but it's relatively close. B is more different than the original, and that's due to the uncertainty. You can look also on the uncertainty of these transport coefficients. This time it will be more interesting. Yes, you can see the V at the edge is very, very uncertain, which also corresponds to the fact that it's so far from the original profile. D is also relatively uncertain at the edge, V over D is as well, and the density profile can move a lot at the edge because there was no single measurements in this point. And here's the correlation between these two, it's highly correlated. That's the most you can say, at least from the information which the covariance matrix provides you. Covariance matrix, during the minimization or Hessian. If you want to get more information, you have to run the Monte Carlo code. So the other option is to go for the experimental data, but setting up the whole experiment will take really a long time, so I have already done it. It's the same as before, just this time I have done some small changes. First, I have switched it to the expert mode. The time step can be varying in the time. So here's the time step, but also each step it will do a small increment in this time step, and it will save every second time step to the CDF file to make it faster. Here's example how it looks like in time. First, there is a very short time step because it's evolving very fast and abruptly after the injection, and later it slows down. I don't need so fast time step just to make the minimization faster. And the radial grid resolution, I have increased the radial grid resolution close to the edge. Close to the edge, it's 0. It's 0. Yeah, this one is in centimeters, so it's 1 centimeter in core and 0.05 centimeter at the edge. The ion it will be aluminum. Impurity source is the LBO injection at 2 seconds. Here's an example how it looks like. Edge recycling, we already know that there is some non-zero recycling for aluminum, so I set the value to 0.2, which is our best guess, but it can also, we can use it as a free parameter during the minimization. Divertor, I have not changed anything here. The transport questions, I started with some initial guess because I already know how the results look like to speed it up, because it can take hours to find some good guess. And the same with for V. V is almost zero everywhere except of the edge, because it was edge mode, so at the edge there will be a huge invert pinch. And the stationary density profile looks like this. It peaks slightly and very steep gradient curves to the escape of flare. It looks trustworthy. There was no salties, and when you turn on the expert option, you can use also Elm model. Elm model means that you will just change the diffusion and pinch during the elms, just for during the duration of the elm. And I will do it in such way that the diffusion will be very large at the edge, and the same as before inside. The same for the pinch. Yeah, the pinch will be the same as during experiment, during sorties. The times of the sorties are loaded from the profile module, so only from QuickFit or from OMFIT profiles. And the duration of the elm is estimated from the signal in the H alpha diodes. So if the elm is large, it usually the duration is longer. If it's small, the duration is shorter. And the time step during the elm increment, or DT increment during the elm, time step after the elm, everything put together, it gives us a very complex time step, like how the time step is changing during the time. During the elm, you can see that it's always short and increasing, short, increasing. That's more or less all. Let's check if it's working. Hope it does. Okay. Let's look again on the I done something wrong. Okay. Yeah. So here is how it looks like. During the elms, you can see it's changing the parallel loss rate. And I was wrong. Because nothing is actually happening during the elms. I have tested everything very carefully. You can see that if there is elm, something tiny happens, but it should be much larger. So let's increase it. Yeah, in time you can see that there are some small drops in the core impurity density, and also issues with the particle conservation during the elms. Okay, but the minimization, there is several new tables which was not there before. In the minimization method, you can select what will be used: Levenberg, Merkvat, Nelder-Met, or Powell's method, or Bayesian sampling for posterior. But this Bayesian sampling is useful, but it is extremely computationally expensive. So don't use it until you will be sure that it's a final solution. the number of iterations and number of CPUs used to doing the calculation of Jacobian and few other parameters. The observation in the current version supports several DC diagnostics, charge change diagnostic, suffix diagnostic, visible Beim-Strahlung, autoradioactive power from bolometers, spread on and CUs. To keep it simple, I will just show the example of the suffix diagnostic. There are two different sources, OMFIT profiles. In this case, it will use line-integrated suffix data, or you can use the output of the Python code, which is a tomographic code. So you will use actual local suffix emissivity. I have used this option. Yeah. Then you have to specify which periodic filter was used. 125 micrometers was in this experiment. The time range used for the subtracting of the background, because if you measure the suffix radiation, you don't measure just the impurity, but also the main ion and carbon radiation. So usually select few milliseconds before the injection for the subtraction of the background. Load data. The Python code will be, I have already written a module for OMFIT, so it will be soon also in OMFIT. Here is the example of data. On the bottom is the temporal evolution, how it evolves in the time. There was injection, fast increase, and then a slow decay, and always a spike during the elm, and the radial profile. It's slightly peaked, hollow in the core, and in the time it's flattening. Yes. So the parameters, that's the most difficult part. Here are defining your optimization model. You can select from almost every parameter, every input parameter for STRAHL. So I have selected just few of them: anomalous diffusion values, anomalous pinch values, the position of the nodes for the position of the nodes for V, and the number of particles. But you can also select any other elms, anomalous diffusion during the elms, anomalous pinch during the elms, and you can also, if you want to fix the value of one parameter to a parameter which was defined before, you can do it this way. For example, in this case, I'm saying that the pinch, the first three nodes of the pinch during the elms is equal to the pinch in between the elms, which is defined before. And the only last value will be varied. The same can be done also for a diffusion.
Really, setting up these parameters is a bit of a
yes,
of an art.
It's relatively difficult. Also for the position of the nodes, in order to make sure that the position is increasing monotonously, you can set that the minimum of in the position of one node is given by the position of the previous node. Which will, this will guarantee that the nodes are in the monotonous order, the position of the nodes. Yes, so now we can start with the preparation. So here is the D which I used. B is very large to be at the edge, huge, and V over D. It's going up to 1 - 100. It's very large, but at the edge, the transport coefficient has a huge uncertainty. So everything is prepared. We can start minimization.
So I'm surprised that you look at the transport of impurities doing elms, like
You have to
just because of the
somehow
challenge.
describe what happens because number of particles is reduced during the elm, and you cannot simply ignore it. These elms are too large, too important.
Yeah. No, I imagine that you would pick times when there was no elms, but probably the plasma is not cooperating.
No.
You don't have the luxury to. I see.
Some people might have that luxury.
That was beautiful about white pedestal, white H1s. There was no elms, so easy.
Right.
Mostly converge already.
So, and I guess here the anomalous transport, you write it as a D and D.
Yes.
But during an elm, it may be, it may not be what we think about microturbulence.
I know, so
it would be something like
the absolute value of the transport coefficients during the elms does not really make a sense. Maybe it should be described by increased power losses in the core of the plasma. Now the power losses are possible just in the scrape flare and outside. During the elm, there can be also power losses from the core. But
it's really like an artificial transport.
Exactly. It's an artificial transport needed just to describe behavior, which we see. Yes, it's done. Hope it was working. Well, it was working really great. Time, yeah, fine. I'm lucky. So here are the suffix profiles evolving in time. You can see that it's matching nicely the timed evolution in the core. Also, radial profile is very well matched. When I look on the temporal evolution, behavior between the elms during the elms is not well reproduced. I was able to do it better, but it would take more time and more playing to find the parameter which gives you which better reproduce the transport in between the elms. What is very interesting, what I found interesting, are these spikes which are following every elm. They are most likely caused by the combination of the cold aluminum when it has left the plasma. It radiates a lot, and this mechanism is probably not included on the STRAHL, or I had to also include time varying kinetic profiles, density and temperature during the elms, which is very, very difficult. Okay.
There's really an inversion in the spike, right? In the functional radius.
Inversion?
If you do a soft X-ray time.
Yes.
Some channels there was a dip. Some channels where there was a spike there.
Yes. Yes. Okay, and now something which can help you to find the good initial guess or give a more intuition what's happening is the interactive fit as the last option. There are two different boundary conditions. You can use the same boundary condition which STRAHL is using, or fix the density to certain position, to the measurements at certain position. And this helps you because you don't have to model elms, which is a great advantage. So I fixed the density to a point 0.8, and here is the GUI. On the left side is DNV. You can move with the nodes up and down, left and right, and look immediately how it affects the suffix radiation. The same with V over D. V over D is changing mainly the radial profile. Here's the radial profile. On the top is on the bottom right is the temporal radial profile, and on the right top is the temporal evolution. And because I have used data just from 0.8 inside, I can ignore these outer points. Yeah, the points are removed by the right button, and you can add new by a middle button. The nodes. These are not important. They are doing nothing because they are outside of the simulated agent. And if you want to look on the time evolution, you can use these two bars. How it evolves into time. The guess is relatively close to the experimental measured suffix data. You can see that elms are really large. So let's start with the minimization. It's done. And now we'll go on the temporal evolution. This black dashed line is the experiment. Black line is the model, and it's matching almost exactly except for the very core. But there is still a large uncertainty. I can remove one of these nodes. I can easily play with the position of the nodes to find out how sensitive is it. Let's add one node here, and you can move it by several orders of magnitude. You should realize that the D is in the logarithmic scale, and nothing is happening. When you reduce it, when it's actually lower, then there is some change. So it's extremely difficult to measure transport coefficients which are not decreasing monotonously inside of the core. If the transport coefficients are flat, or they are maybe even increasing towards the core, it's almost impossible to measure them. There is a huge uncertainty. And V over D, if I will vary the core,
this is because you're using soft X-ray. If you were using a different diagnostic, which is it? Okay.
Yes. It's just the property of the diffusion equation. This D simply tells you what's the delay, how much is the delay between different position increased. If the D is small, the core values of the emissivity are delayed more. If D is very large, it's delayed less with respect to the inner radial position, but there is no difference if it's delayed 1 millisecond or 0.1 millisecond. You will not be able to measure it. Yes, so let's try it again. It's only 2 nodes. You can also estimate the optimal number of nodes using this method. This V over D, and it's really able to have very nice fits. And you can look on the uncertainty of these vector profiles. If the covariance matrix is too ill-posed or singular, it's not possible to calculate the uncertainty. So this is more a solve which I have prepared for this tutorial.
Yeah, I think it was pretty comprehensive.
So if you have any questions,
I learned a lot. Yeah, no, very nice, very nice. Yeah, I used the STRAHL for these, coupled simulations. I have not used it the way you are.
For the inversion task.
Yeah, exactly. But yeah, I can see how. Because STRAHL just does the forward problem, right?
Yes.
So actually, there is a lot of work that's happening
in the
behind the
experiment,
scenes.
you actually have to use multiple diagnostics. You have charge and suffix array spread, and all of them gives you inconsistent information. Like it's not possible to fit them all exactly, which makes it even more difficult.
So it's already very complete and not easy to set up within OMFIT. How are different devices doing it? Like if you go to CMOD, but also Aztecs, where for example the guys who develop STRAHL.
They are not running the same version problem, or if they do it in a very simple way.
So even the guys who develop STRAHL, they're not using it really in this inversion.
Yes,
people I think are using
Ralph
optimizations and chi-square equations.
Yeah, Ralph, he has developed it and he has never used it in this optimization. He had another tool just to solve the like the one which I have shown you, this interactive fit, which was solving it, which was calculating just the total impurity density. Yeah, I forget to show this. Once it is done, you can run the STRAHL again. It will update the dependence between the suffix emissivity and the impurity density, but it should be just small change, and you can find a new set of transport coefficients in 2 or 3 steps, which should converge to the final value. That's what Ralph has done with what he was doing for his research. He has also fixed the density to a certain position and calculating just the total impurity density correcting interactive with STRAHL.
So this interactive fit or interactive GUI uses an approximation.
Yes, yeah, exactly.
Which is that you're only.
I'm only calculating the total impurity density. That's the reason why it's so fast.
I see.
In STRAHL calculates the density of all ionizations.
And you're not running.
Ions.
You're not running STRAHL when you run this interactively, right? I didn't see any.
No.
So
I ran a Python code which is using the same numerical scheme as STRAHL, just because of the simplification, it's faster.
I see. Okay. And the atomic data you get from the ADAs, or
in this case, I don't need atomic data. Everything is.
Because it's the total.
Yes, it's a total density. In this case, no, I don't need any combination rates, ionization rates, and the dependence between the total suffix emissivity and total density is estimated from the STRAHL around, which will sound from the same transport coefficient.
Some people have also tried to estimate PND without doing a minimization.
Yes, often what was done a long time ago, there was just guessing, changing by hand, changing.
That was a stage. And Sartori's paper was presenting the
gradient flux method.
Okay.
That's another alternative. But
other approximations.
It's as crude approximation as this one, the one which is used in the interactive field.
So, and how hard do you think would be to, if there are other people interested in doing this, as the expert by Jay, how hard would it be to adapt this?
The first part is how the minimization is real trivial. Just load different atomic data, load different equilibrium, load different kinetic profiles.
Which is kind of already what I was doing, because I was running it for ITER. So it's running STRAHL for a different machine is easy.
You have to create the grid file.
Right.
Code. Any machines like that.
The minimization is difficult only from the point of view of these observations.
So it's really hooking up the experimental observation.
Yes, because every machine has a unique set of the diagnostics.
Right.
Even two suffix A diagnostics are not equal.
Right.
But I would say this is not a module that you can just plug and play. There's a lot of detail in the diagnostics that has to be resolved. The small differences are what determines.
Yeah, because these are effectively synthetic diagnostics.
Yes.
That you have there.
Yeah. So you need a synthetic diagnostic for every.
That's pretty good.
We have how important is the neoclassical calculation?
It's using just n class model, which is relatively simple, but it has advantages extremely fast. So you can calculate. Ralph has calculated the neoclassical transport during the ELMs, time-evolving transport coefficients. You can include also during the ELM, it flashes the impurities, changing the ratio between oxygen and tungsten and carbon, whatever is there, and this is changing back the neoclassical transport coefficients. So you can run it in this in the way where the impurity is changed by the neoclassical transport is changed back by the impurities. But I would recommend to use NEO. It should be more accurate.
That's what I want.
And for impurities, well, so you have obviously the neoclassical and the turbulent.
Yes.
So what's the relative importance between these two? The two.
Inside of the core, and for high Z impurities, it should be neoclassical.
Okay.
For low Z impurities, carbon, turbulent, probably everywhere, or maybe. That also depends. If you have a lot of ion heating or extremely large amount of electron heating, but let's say just lots of ion heating, then it is mostly neoclassical in the core to mid-radius, let's say. Also, it depends on the Q profiles. It's very sensitive. The transport coefficients are very sensitive on the parameters of the plasma. It's changing by order of magnitude, several times more than the transport coefficient for the heat.
Yeah, maybe one comment is I remember at maybe it was TTF. I remember you were telling me that the turbulent transport for impurities doesn't change much with the type of impurity.
No, yeah, what I have found is the modeling, and also probably with the experiment, it's very difficult to say if it's the same in the experiment or not, but it should be almost the same.
Okay.
Behind the test.
Okay. But in the core region, the turbulent transport for
I can show the scan which I have done using STRAHL, just a linear STRAHL. Here's the element. I have calculated the charge for 3 kiloelectron volt, and the mass is given for each element. So when I was doing the scan, both charge was changing and the mass was changing for each element, but for some certain temperature. And you can see the full line is one full line is aluminum, the second full line is the right is the tungsten, and the fusion coefficient between these two for all 3 cases, blue, black, and red, is exactly the same, or just few percent difference.
The colors are different, different plasmas.
Different plasmas, yes. The red, it should be in ITG. The blue should be TM, emanated plasma.
And they're fairly flat. So.
Yes, it's really flat. And the 3 other plots are showing pinch, different components, just pinch, thermal diffusion, rotor diffusion. But if you sum it everything together, it's almost constant. There is no difference between these impurities. So the only difference comes from the rotational physics, because the tungsten can have a large Boyle asymmetries. If you actually calculate not the low field side impurity transport coefficients, but the flux impurity transport coefficient for the flux surface impurity density, there will be a difference, but it comes only from this effect.
Okay. Cool.
And the same prediction I've
And
done.
the effect is part of STRAHL.
Yes, it's including STRAHL.